Maybe. Because of Professor remember that. What's his name, brother? The younger one, no.
Got Mario to come to this. No, he didn't come very often.
Okay, let's get started. Have your attention. It's my privilege to welcome you to the University of Tennessee Nuclear Engineering Department Seminar Program. Today's speaker is Dr. Charles Forsberg, who is a distinguished staff member of the Oak Ridge National Laboratory. Charles received his BS degree in chemical engineering from the University of Minnesota and a PhD in nuclear engineering from MIT. He's been a longtime friend of this department. I dare say Charles has presented as many seminars over the past 25 or 30 years as anybody, and we're always appreciative of his efforts, and he does really interesting work, and today's topic is no exception. The title of this presentation is the Advanced High Temperature Reactor for Electricity and Hydrogen Production. Welcome, Charles.
Thank you. Well, the title's already been explained to you, but I'd also like to acknowledge some work being done by both myself and some people at Sandia. It's sort of a cooperative effort to develop a new concept of a reactor, both for electric production, but also a reactor that can meet the very specific and tight requirements associated with thermochemical hydrogen production. And don't worry, I'll explain what that means about halfway through this talk. Oops. Okay.
Push the forward arrow.
Whoops, I did something. I did something wrong. There we go.
Keep the mouse out there.
Okay. I'd like to discuss first what an advanced high temperature reactor is. It's a new concept for a reactor. And I'd like to discuss the application, because one of the issues of a new reactor is how you use the heat from that reactor to make electricity and hydrogen production. Just going backwards, let me go back. I'll just continue on. First, I'd like to discuss the high temperature reactor. The high temperature reactor has two defining characteristics. It separates it from other reactors. First, the fuel is coated particle fuel. This is a graphite fuel, similar to that used in the high temperature gas-cooled reactor. The second and other defining characteristic is it uses a molten salt coolant, a fluoride salt. Now I'll discuss that in a little bit further detail later. The important item to be noted is that when you combine this particular fuel with this particular coolant, one obtains some very unusual characteristics for an advanced reactor. Here's a very simplified schematic of the reactor. Here's the reactor core, which of course is a graphite core. Molten salt goes through an external loop to a power cycle or a heat exchanger where heat is used to make hydrogen production, or electricity using a Brayton indirect cycle or a direct thermoelectric cycle. Molten salt then goes back to the reactor. The reactor also has a passive cooling system that I will describe in later detail. The particular salt, baseline salt, is a lithium beryllium fluoride, but there are several other possible fluoride salts that can be used. Now, I should mention something about fluoride salts that most people don't realize, and that is there's a very large industrial base with fluoride salts. The process used to make aluminum, like an aluminum tin can, is electrolysis of a fluoride salt. Well, there's industrial experience in using fluoride salts at about 1,000 degrees C since about 1895. Not exactly the newest technology on the planet Earth. As I mentioned earlier, the advanced high-temperature reactor combines two technologies to produce high-temperature heat. First, the coated particle graphite fuel. This fuel has a very interesting characteristic. Demonstrated temperature limit is 1,200 degrees Celsius. It's the same technology that's used for the modular high-temperature gas-cooled reactor. The second characteristic is the molten salt coolant. Two possible coolants are the lithium fluoride, beryllium fluoride coolant, and the sodium fluoride, zirconium fluoride coolant. These coolants have some unusual characteristics. First, the boiling point is near 1,400 degrees Celsius. Second, they're very efficient for heat transfer. Heat transfer properties are similar to that of water. This allows a significantly higher reactor coolant exit temperatures for the same fuel temperature limits, as I will describe later. Third, these are the same coolants that are proposed for fusion energy reactors, both the inertial confusion and the magnetic fusion reactors. Last, these particular salts were originally developed as part of the aircraft nuclear propulsion program. Now, that program wasn't a particularly successful program in terms of producing a nuclear-powered aircraft for some very obvious reasons, weighed too much. But there was a very large development program to develop molten salts, including molten salt heat transfer loops, molten salt test loops, and measurement of the physical properties of molten salts. Let me briefly describe the high-temperature fuel for those of you who are not familiar with HTGR fuel. The high-temperature fuel has uranium oxide or carbide in a very small sphere with multiple coats that isolate the uranium and fission products from the environment. These microspheres are about 1/8 of an inch or less in diameter. The microspheres are put into a matrix of carbon. We get a carbon matrix with microspheres in it. Carbon matrices are put into a fuel pin. The fuel pin is put into a graphite block. This particular example of a graphite block is that proposed for the Japanese high-temperature engineering test reactor. It's designed to operate at 950 degrees Celsius. Now let's take a look at coolants for reactors. We want to have a high-temperature reactor. We want low pressures for obvious safety and other reasons. Let's take a look at the temperatures of various reactor coolants. Well, of course, with the traditional, whoops, let's flip backward, go back one. The traditional coolant is water for water-cooled reactors, a boiling point of 100 C. This, of course, is too low to generate significant energy for electric production, so we pressurize the system and operate at 200 to 300 degrees C. A number of reactors have been operated with sodium. Sodium has a boiling point of 883 degrees C. Again, we'd like to operate between 750 and 1,000 degrees C, so we're looking at molten salt coolants with a temperature boiling point of around 1,400 degrees C. Now, as I mentioned earlier, there are many types of molten salts. Some molten salts have boiling points of 1,300 degrees. Some have 1,500 degrees C, but they're all within a 100 or 200 degree range of 1,400 degrees C. If we use this type of coolant, we can safely say the coolant is not going to boil. So we have a nice liquid coolant, very low vapor pressure a fraction of an atmosphere during any kind of conceivable operation. I'd now like to discuss the fuel and the implications of the fuel and using a liquid coolant. I make the following observation. The temperature drop between a fuel and a coolant depends upon the fuel design and the coolant. In the next slide, I'm going to show you some numbers. I'd like to first point out, though, that if you're building a graphite reactor, you can make several kinds of fuel. You can make hexagonal blocks. You can make it in a form of a central cooling channel where you have an annular fuel zone with a cooling channel in the middle, or you can have pebble bed reactors, where the reactor has microspheres in a ball of graphite about the size of my fist, and you just fill up the whole reactor with these fist-sized balls until it's completely full. Many different fuel designs, but the same basic concept, microspheres embedded in graphite. Now, let's take a look at what the implications are of using a liquid coolant, a high-temperature fuel. The important point here is that the temperature drops from fuel to coolant depend upon the coolant. Here we show a number of fuel element configurations, hexagonal block, central cooling channel, and pebble bed. Here we show the temperature drops between the hottest point in the fuel, the very hottest point in the fuel, and the liquid coolant, or the gaseous coolant, whatever the coolant is. And for a high-temperature reactor with a hexagonal block, the maximum temperature drop, delta T, is 415 degrees C. That is, the microsphere of uranium at the center is 415 degrees C hotter than the helium in the middle of the channel, of the coolant channel. In comparison, if we put in molten salt in the same type of fuel element, the temperature difference between the hottest point in the fuel and the coolant is 280 degrees. The reason why the temperature is lower is that liquids are better cooling. It's easier to cool a person with liquid. Here's a very simple example. If I throw a bucket of water on you, you will cool down much faster than if I come out and take a fan to you. Same principles. Bucket of water versus a fan. That's why the temperature drop between the fuel and the coolant is much less for molten salt. Now, what does this mean? We take our high-temperature reactor, we have a 415 degrees C, and we put molten salt in. We're now down to 280 degrees C, or we've lowered the temperature 135 degrees Celsius. So we can have the reactor with the same exit temperature, but the fuel will be 135 degrees cooler. Alternatively, we can say, we'll run the fuel as hot as we previously did, but we'll use that extra temperature drop to increase the temperature of the coolant and increase the temperature of the coolant by 135 degrees for the same fuel limits. Heat transfer 101. The important difference between a liquid coolant, throwing a bucket of water on top of somebody, versus a fan. There's another implication of using liquid coolants versus gaseous coolants. I'd like to observe that the reactor efficiency depends upon the temperature at which the heat is delivered. Now, this particular slide shows the temperature of the coolant coming out of the reactor and going through the outside exterior heat exchanger to the power cycle or hydrogen production system. And we show here a number of existing and proposed reactors. For example, if we take a look at the British advanced high temperature or British gas-cooled reactor, one of which there are about 15 in Europe that use carbon dioxide cooling, such as Hinkley Point B, we find that the exit temperature of the reactor is 665 degrees, and the inlet temperature to the reactor is 310 degrees C. There's a big temperature drop, over 300 degrees Celsius. If we look at the proposed high-temperature gas-cooled reactor, the exit temperature is 850 degrees, and the entrance temperature is 491 degrees. 360-degree temperature drop. Why the large temperature drop? Well, it takes a lot of energy to pump gases. It needs very large compressors. And to make sure that the energy losses in the compressors are minimal, the energy consumption by the compressors are minimal, what we do is we take large temperature drops. If we had a small temperature drop across a gas-cooled reactor, the horsepower required by the circulators might equal the power output of the reactor. Highly undesirable affair. Well, let's compare this to a pressurized water reactor, a liquid-cooled reactor. And I've used this example, the Point Beach reactor, which is in, I think, Wisconsin, if I remember correctly. And we find out that the exit temperature from the reactor core is 319 degrees C, and the temperature going back in the reactor core is 299 degrees C. There's a 20 degrees Celsius temperature drop from the inlet of the reactor to the outlet. That means that this reactor is going to deliver almost all of its heat at a constant temperature. We design liquid-cooled reactors this way because it doesn't take a lot of energy to move water. It takes a lot of energy to move air, but very little energy to move water. It's a characteristic of liquid cooling. Well, what does that mean in terms of our advanced gas-cooled or advanced high-temperature reactor with sodium cooling? Let's compare our advanced high-temperature reactor operating at 750 C with a proposed high-temperature gas-cooled reactor operating at 850 degrees C. So we'll give the HTGR a 100 degrees C advantage over us. Well, HTGR certainly delivers a lot of heat, delivers the initial heat at 850 degrees C, and then the next heat a little lower until we get down to 491 degrees C. If you look at the average temperature of the heat delivered by the HTGR, why, it's down there about 700 degrees Celsius average. Now let's take our advanced high-temperature reactor with a liquid coolant, and that's the important thing. It happens to be a molten salt, but the really important thing is it's a liquid coolant, and it's operating with an exit temperature of 750 degrees C. But the pumping horsepower is low, so we can deliver most of the heat at high temperature. Now, isn't that interesting? The average heat delivered from a a molten salt cooled reactor will be higher than from an HTGR, even though the exit temperature from the reactor is 100 degrees C less. Miracles of liquid cooling. As I say, we're talking about a molten salt reactor, but any other liquid would have similar properties. The only reason I like molten salt reactors is I'd like an unpressurized reactor, and at 1000 C there aren't very many unpressurized materials that are liquids. Well, let's take a look at the implications. This has some very important implications in terms of electric production and more important implications in terms of hydrogen production. I'm going to start with the electric production. That's relatively simple. Then I'm going to turn to hydrogen production, where the ability to deliver all of the heat at high temperature is the important requirement. Here's the advanced high-temperature reactor for a power cycle for electric production. It uses a multi-heat Brayton cycle for high-efficiency electric production. This is the Brayton equivalent of the steam cycle used at a coal-fired power station, such as Bull Run or Kingston or any of the other TVA coal-fired power plants. Here we have the reactor core, hot molten salt, and a helium cycle. This helium cycle is a little bit different than the traditional helium cycle. It's a reheat cycle. The cold helium comes in, it's heated to, let's say, 750 degrees C, goes through a turbine, is partly let down in pressure, is reheated to 750 degrees C, goes through a second turbine, reheated, and goes down through a third turbine. In effect, the turbine operates, for the most part, at very high temperatures because of this multiple reheat cycle. The helium is then, of course, cooled, goes through recompression, solid-state recompression, and back to this multi-reheat cycle. Now, the ability to deliver the temperature, the heat at a high temperature and use it has some powerful implications in terms of thermodynamic efficiency. That is, how much energy we convert to electricity. The AHTGR, an advanced high-temperature reactor, delivers all of the heat at high temperatures. That implies high electric conversion efficiency. Let's assume our exit temperature is 750 degrees C for molten salt. For this cycle, our thermal efficiency will be 48 degrees. Important point, why I keep mentioning 750, is this is the temperature where we have existing materials that we could build this reactor out of. I'd like to operate it hotter, but I'd have to develop new materials. Now let's take a look at 850 C. The efficiency would go up to 56%. Now, it turns out at 850 C that the MHTGR, actual efficiency at this temperature, is 48%. So what you see here is that if we operate at the same temperature as an HTGR, we gain about 8 percentage points efficiency. And it's because we deliver all the temperature at the maximum possible height. If we go to 1000 C, we can build a Brayton cycle with 59% efficiency. This type of efficiency, of course, requires new materials. There's just no way around it. None of the existing materials are currently suitable for these temperatures. Talked about electricity briefly. I'd now like to talk about hydrogen. Hydrogen may be the wave of the future, but hydrogen is tough to make. And I'd like to go first into some of the reasons why I want to go toward a hydrogen economy, and second, how you make it using nuclear energy. The first observation is there's a growing hydrogen demand. Worldwide, we use about 50 million tons of hydrogen. There are multiple hydrogen pipelines in the United States and Europe. The two major applications are, first, the production of ammonia. That's the primary fertilizer used in commercial agriculture. And second, the demand for refineries to produce transport fuels. Now, that needs a little bit of explanation. If you read the newspapers, you keep hearing that we're using poor quality oil. Crude oil quality is going down. Well, what does that mean? Today, we're importing a lot of crude oil from Venezuela. This is what they call heavy crude oil. Now, if I took a peanut butter jar of heavy crude oil at room temperature, undid the lid, put it upside down on this table, or put it on the floor, which would make Professor Dodds even more unhappy, it is quite likely that the floor would not, or the table would not be marred during the completion of the rest of this talk. This stuff is thicker than peanut butter. Now, fortunately, it comes out of the well at about 200 C, so it's pumpable when it comes out. When it gets to room temperature, it becomes sort of like Skippy peanut butter. Not very useful as a transport fuel. Well, the way you convert it into a transport fuel is you add lots of hydrogen and change the hydrogen to carbon ratio to make gasoline. Similarly, if you want to make clean gasoline, you add more hydrogen. So we have, in a certain sense, a very large hydrogen economy today. It's just that we hid it away at the refinery. And this is an economy that's growing at a rate of 5 to 10% a year because our crude oil supplies are becoming worse and worse. We're getting more cruddy crude oil. That's not going to change. Now, in the longer term, there's the future hydrogen economy. As most of you may be aware of, the President of the U.S. and the Department of Energy has initiated a national program to develop fuel cells for automobiles. Fuel cells use hydrogen. In the near term, they may use gasoline that's converted to hydrogen on board the car, but in the long run, we'll obviously fuel these with hydrogen. If this demand occurs, the demand for hydrogen may approach, in terms of energy value, may approach the energy content that goes into electricity. So we're talking about a very large demand for hydrogen in terms of energy, roughly equivalent to that of the electric market. So it's obviously a very important energy market. Well, that's the good news. Now let's go to the more complicated world. Hydrogen can be produced with heat from a nuclear reactor. There are lots of theoretical studies that have been done to indicate that this is the cheapest way to make hydrogen. Basic reaction is quite simple. Heat plus water, that's supposed to be yields hydrogen plus oxygen. That's the good news. Now for the little troublesome details. The characteristic of making hydrogen from water. First, the good news is projected thermochemical efficiencies are about 50%. That's really rather nice. And the complication. High temperature heat, 800 to 1,000 degrees C, is required for thermochemical methods. This is the same temperature range that's used to convert methane into hydrogen in current hydrogen production plants. All the ways to make hydrogen except electrolysis require high temperature heat, and electrolysis turns out to be a very expensive way to do business. In short, we can make it, but there's a little catch here, 800 to 1,000 degrees C. And of course, that is one of the reasons why we're looking at the advanced high-temperature reactor, because we need to be able to deliver all of that heat at a high temperature. Now, for those of you who are chemists or chemical engineers, I thought I should explain what a thermochemical cycle is. If you had first-year chemistry, this may be quite straightforward. Important item here is the heat input is 800 to 1,000 degrees C. The output is oxygen and hydrogen. The input is water, the the heat. We have two sets of chemical reactions, and these two sets of chemical reactions have lots of chemicals that go around in circles, but the net result is heat plus water equals hydrogen plus oxygen. All of the other chemicals go around in an endless circle. The example cycle that I've chosen to describe here is the iodine-sulfur process. Let me briefly explain what that is. The starting chemical reaction, the high-temperature chemical reaction, is the dissociation of sulfuric acid into water, sulfur dioxide, and oxygen. Well, the oxygen is the product, so we take that off, and then what we have left is sulfur dioxide. We combine sulfur dioxide, water, and iodine to make hydrogen iodide and sulfuric acid. Well, the sulfuric acid goes back here to make more oxygen. The hydrogen iodide goes through the secondary loop. The hydrogen iodide is decomposed into hydrogen and iodine. Hydrogen, of course, is the product. The iodine goes back in this cycle to continue the process. So we have two coupled chemical reactions with a net result of heat plus water plus oxygen plus hydrogen. The catch is that this reaction is a high-temperature dissociation reaction where the heat has to be provided all at high temperature. It does no good to provide heat at 700 degrees Celsius. Worthless for this process. With that, I'd like to now discuss a couple of other issues that are important for any type of nuclear reactor, and that is safety and economics. The safety case for the AHTGR, and I'm going to describe two issues here. First, accident prevention, and then accident control. Power levels are limited by the inherent design of the reactor. It has a negative void coefficient and a negative Doppler coefficient. Secondly, coolant properties increase the safety margins. We have a natural circulation of coolant removes radioactive decay from the reactor core to the heat sinks. It's a liquid. You heat it up, natural circulation loops will circulate the heat around to the vessel. We have efficient heat transfer, which minimizes the temperature rise of fuel during off-normal conditions. We have a high heat capacity that reduces the rate of core heat up during off-normal operations. And we have a very large temperature margin, 400 degrees C, between the coolant operating temperature and the boiling temperature. I'm going to briefly mention something about the reactor core physics of this particular reactor. This particular view graph that I'm not going to go into detail shows the thermal flux profile of a particular point design of the advanced high-temperature reactor and of the helium-cooled high-temperature gas-cooled reactor. It turns out that molten salts have very low nuclear cross-sections. They're almost invisible to neutrons. So we have a graphite core that looks like an HTGR core. We've changed the coolant out, but the coolant is neutronically invisible. What that means is the reactor physics of an HTGR and of an advanced high-temperature reactor with molten salt are almost identical. There's some minor differences, but they're not major differences, and that's because the salt is almost, not quite as invisible, but almost invisible to the neutrons. The salt cross-sections are about 1/10 that of water coolant, much below water, so it's almost invisible, but not quite. The other issue, of course, for reactors is what do you do in the case of an accident. I'd like to briefly describe the safety case for the advanced high-temperature reactor. First, of course, we have a low-pressure atmospheric coolant. That's very important in an accident scenario because escaping pressurized fluids provide the mechanism of radioactive transport from the reactor during an accident. Low-pressure salt coolant minimizes accident potential for radioactive transport. Second, the molten salt is a secondary barrier to prevent the radionuclide releases to the environment. Now, about 30 years ago, Oak Ridge National Laboratory developed something called the molten salt reactor. Different concept. In that concept, you dissolve the uranium in the molten salt. And when it fissioned, the fission products were in the molten salt. And the reason they use molten salts is because molten salts have a very high solubility for uranium and fission products. Now, in our case, we're using clean molten salt with no fission products in it. But if fission products do escape from the fuel, we'll expect them to dissolve into the molten salt. So the molten salt acts as a secondary barrier to any releases from the fuel. Ideally, there's no releases from the fuel, but we have this secondary barrier. The third feature is that we can use passive decay heat systems similar to those proposed for the liquid metal reactor, in particular the S-prism. I'd like to briefly describe this because it's a very interesting characteristic of this reactor that is very, very unique. The advanced high-temperature reactor and proposed modular liquid metal reactors use the same decay heat removal system. In particular, we're using the one that's proposed for the General Electric S-prism reactor. And let me briefly explain how this works. Here we have the reactor vessel. And of course, heat in an accident is transferred from the reactor core by natural circulation to the reactor vessel. The reactor vessel sits in a second vessel, a guard vessel. That's the second vessel here. And outside the guard vessel is the natural circulation of air from the atmosphere by the guard vessel outside. Now, during normal operations, the amount of heat loss from the reactor to the outside environment is very low because the heat has to go from the primary reactor vessel to the guard vessel. And between these two vessels is about 4 inches of argon gas. The only way the gas can go across here is by radiation heat transfer. It's sort of like a sun lamp. Go put something under a sun lamp. Same philosophy. Now, what's important about heat transfer by radiation is that the amount of heat you transfer depends upon the temperature to the 4th power. So a very small increase in temperature results in a massive increase in the amount of heat that goes from the primary reactor vessel to the secondary reactor vessel. It's a fluidic, it's a solid state thermal switch mechanism. Low heat loss at one temperature, very high heat loss if the temperature goes up 50 degrees C. And of course, people have worked out the details of this for the prism reactor of General Electric. There's one other interesting characteristic about this. General Electric has done a lot of design work on this reactor, on their liquid metal reactor. And in the case of their liquid metal reactor, where they have temperatures of 500 to 550 degrees Celsius, they have discovered, after lots of calculations and experiments, that the maximum size of their reactor can be about 1,000 megawatts electric. And the reason why is that they go to higher power levels, there's simply not enough surface area in this vessel to transfer the heat in an emergency across to the air-cooled system. So the limit to this air-cooling system in a liquid metal fast reactor or some other type of reactor in the same temperature range is about 1,000 megawatts. However, we're not proposing to operate at 1,000 megawatts. I mean to 550 degrees C. We're proposing to operate at a minimum of 750 degrees C and perhaps to 1,000 degrees C. As I mentioned, the heat transfer goes up as T to the fourth, temperature to the fourth. That means where this reactor design and passive cooling system can remove, really pushing it, maybe 1,000 megawatts at 550 degrees C. At 750 degrees C, we can handle the decay heat from 2,000, perhaps 3,000, perhaps even 4,000 megawatts. Certainly at least 2,000 megawatts. With our 50% efficiency, that means with a molten salt reactor, we can have a passively cooled reactor producing 1,000 megawatts of electricity. Now, all of the other passively cooled reactors that people have proposed have an electric production capability of about 300, 350 megawatts each. We have a reactor that can produce 1,000 megawatts of electricity with a passive cooling system. So because of the nature of our reactor, the nature of the liquid coolant, the nature of radiation transfer, we can build large reactors with passive cooling systems, something that has not been previously possible. And this may have some very large economic implications. I briefly mentioned the economics. The economics are potentially very attractive. And all of the economic benefits flow from this fact that we have a liquid-cooled reactor combined with a high-temperature fuel. It's that combination that is critical. Pick another high-temperature fuel, another liquid reactor, you come up with the same conclusion. It's that combination that makes it interesting. First, a large reactor may be possible, 1,000 megawatts with passive decay heat cooling systems. And that's a very unique characteristic of this reactor concept. It also may allow the economics of scale. Second, we can use high-efficiency, multi-reheat breaking cycles. It's a unique characteristic. I believe this is the only reactor concept that has ever suggested or proposed a multi-reheat breaking cycle, although the multi-reheat Rankine cycles, steam cycles, are the standard cycle used in the coal industry. The high temperatures imply smaller cooling systems and smaller equipment compared to traditional steam cycles. Well, where does that leave us? The first thing that's obvious, for those of you who are familiar with the history of nuclear power, is what we've done is we've pasted together 4 technologies developed at different times in the history of nuclear energy to come up with a new reactor concept. This concept could not have existed 10 years ago. We have stolen, borrowed, begged, whatever the term we wish to use, the molten salt coolant technology from the aircraft nuclear propulsion program of the 1950s. We've taken the gas-cooled high-temperature fuel technology of the 1970s, didn't find any technology in the 60s we were interested in, added the liquid metal reactor passive decay heat cooling system of the 1980s, and the helium gas turbine technology that has come into existence in the 1990s. So it's a mixing and blending of 4 old technologies that have been partly developed to create a new nuclear energy option. I think this is important because you have to recognize when you talk about new reactors is that new options become available as the technology progresses. And this is a classic example of a technology that could not have been proposed 10 years ago because key components were missing. And I'm sure there's some other concepts out there, similar things. The AHGGR has potentially unique capabilities. Most important is all the heat is delivered at high temperatures. That's absolutely critical for hydrogen production, and it's certainly highly desirable for electric production. And second, it has large passive cooling systems. Last, and I certainly should emphasize this, it's a new concept with many options. We may or may not have the right system configuration. There may be other ways to put the system together. And of course, it also implies, since this concept is maybe 14 months old, a great deal of uncertainty. We're still learning what the reactor can do, what it cannot do, and we have a long ways to go before we have a conceptual design that you could take to a vendor or that you could have a review panel look at and say, yes, you've got all the pieces in place. It can be built. With that, I will end and open up the floor for questions.
Okay. Do we have questions or comments for Dr. Forsberg?
Yes.
What material? You said you need a new material to be operating at this high temperature.
At 750 C, we believe Hastelloy N will work. Above that temperature, we believe new alloys of construction are required. There are a number of alloys in the laboratory that can operate at 1,000 degrees C. but we are a long ways from those alloys being useful in an industrial sense where people can manufacture them in large quantities and weld them, and that they have proper code stamp. 750 is what I would call a near-term capability with materials that you can weld, reasonably understood, and where there is a code certification for.
What temperature do you need for hydrogen then?
Hydrogen, you need probably a minimum of about 800, which means we're going to have to improve the metallurgy. As you can see, we've chosen two temperatures. One, we can make electricity today, and then we've looked at another one where, yes, we're going to have to get better materials. As I say, there are materials in the lab. It's just that they are not to the point where you could use them in an industrial application.
What are the temperatures that are out of the conventional gas turbines? Are they not quite a bit higher than that? And what materials are they, or are there corrosion problems?
The gas turbine, there are two items to be remembered here. The gas turbines, or for that matter,
I mean, just gas turbines
in general, have two things going for them. First, many of the turbine blades and many of the components in that gas turbine are actively cooled. That is, they have cooling coils or cooling channels inside the middle of the blades, and that's certainly fine if you want to replace your equipment once a year. Not so good if you want to replace your equipment every 40 years. The second issue is, of course, this issue of maintenance. People who own gas turbines buy turbine blades as like razor blades. They're a disposable item. And if you're talking about base load electricity where you're going to be running this turbine day after day after day, 300 days a year, you do not want a situation where you have to shut down every couple of months for a turbine replacement. So it's the difference between application. Remember, most gas turbine applications for power, natural gas to electricity, most of these units are not running base load. They're running as peaking units. So
but they run at about 2,000 degrees Fahrenheit.
Right, that's right. But they replace blades like they were going out of style. And that's economic to do, but we have some doubts on whether that's a viable option for a base load nuclear plant.
What about the hydrogen production that goes on now? What do they do?
They replace tubes regularly. They go into their boilers, strip them out, put new tubes in. You can do it. You can do it, but the question is how will that impact the economics? There's some other issues associated with nuclear. The downtime for nuclear is going to be more expensive than the existing plants. But right now, what people do on these high-temperature applications is they essentially have throwaway alloys. We use them for a limited amount of time and cut them out and replace them. And there's some questions on the economics of that.
What about aircraft turbines and airplanes? What do they run at, and how long do they last?
That depends on how much junk you throw in them. If you have any junk, they disappear. I don't know, what are they, a couple of thousand hours? It's not very many. If you go down to Atlanta, you'll find that Delta has this tremendous engine shop. And their engines regularly visit their engine shop.
Mo?
I guess the question is, what are other current methods of producing hydrogen? How will this compete economically with them, given all the uncertainty about material production, new material you're going to need?
Almost all hydrogen worldwide is made by steam reforming of methane, which means you're really asking me to predict natural gas prices 20 years out. It's clear we would compete in some parts of the world. It's clear we would not compete in other parts of the world with natural gas. But if you start talking 20 years out, you have to ask yourself what the price of natural gas is going to be.
I mean, you mentioned that, like material production, you're going to need new metallurgical techniques and new materials and things. I just thought that might drive your cost up of being able to produce hydrogen.
The development cost will be high, but one expects the long-term production costs to be low because nuclear power has low fuel costs. There's one other thing that's very important about these hydrogen thermochemical methods. In the long run, they have the potential that, although you have to work through the metallurgy, to be very cheap. And the reason why is inside these loops, you have very pure chemicals. The way you make hydrogen today with steam reforming is you put in, natural gas, you put in air. With the air, you get all sorts of other wonderful free ingredients. And those free ingredients tend to tear up your hydrogen plant, which means regularly they come along and cut out whole sections and replace it. So in the long run, I think that the potential is that we can be substantially less expensive than the existing plants that have this problem that they keep pouring in pure materials into their plant. That's the economic thing to do. And they keep corroding away hydrogen plant. Hydrogen is expensive for very good reasons. It's not just the natural gas. It's the fact that they're very high maintenance operations to make hydrogen from natural gas. These are really big, expensive chemical plants.
Yes, in the back.
Just going back to when you had the reaction of heat plus water to give off oxygen and hydrogen, can that be reversed to just give energy and water?
Yes.
Or is it too hard to come by?
That's called a fuel cell. That's the fuel. The fuel cell works in the reverse direction. Or actually, you can make electricity with the fuel cell. You can burn hydrogen. There's no problem in the reverse direction. Hydrogen burns beautifully.
Why is that not used more? Why is that not used more? If you could just make a lot.
You can't make. You can't. It's expensive to make hydrogen. That's why you don't use it as a fuel. Hydrogen is very much of a premium fuel. You don't use hydrogen for heat. You use hydrogen in fuel cells to directly produce electricity. Hydrogen is the premium, is a premium fuel like electricity. Very much of a premium fuel.
How reactive are these salts at temperature if they're exposed?
They are not reactive with air or carbon dioxide. They are slightly reactive with water. It's a slow reaction. This is not sodium. So.
It produces oxygen. Is there any kind of economic implication of that? Is there a use of the oxygen?
I think you have to ask what the time frame is. In the near term, there is a large demand for oxygen. If you had relatively low-cost oxygen, every sewer plant in the country would love to have it. You'd shrink the sewer plant by about a factor of 5 using pure oxygen rather than air going through it. In the long term, I suspect there's not much of a market for it, because if you are producing half the world's energy and converting it into hydrogen, you are producing absolutely incredible quantities of oxygen. I think what will happen is you'll totally saturate the market. But that's maybe 100 years off. In the near term, yes. In the long term, it's saturation time.
I'm just curious. I mean, I talked to John Getty. I think he was working on some things too a while back, and he was kind of working on something similar to hydrogen production and things like this. And he was kind of looking at some like microbiology organisms, things
Yes.
like this. And I mean, has that ever come through? Like, you can use like certain enzymes and things like this.
Yes,
to
yes.
produce hydrogen.
Yes.
To
Yes,
large scale.
there's a fair amount of work, including work at Oak Ridge National Lab, to turn biomass into hydrogen. It may, if they can develop the technology, and that's a very big if, it may be attractive in some markets where you have a lot of available biomass. However, for most of the industrial world, land is a constraint, and biomass is a major constraint. So, for Japan, Western Europe, Eastern U.S., these are areas where there isn't enough biomass to go around. Any area with high population densities.
Dan?
I wasn't supposed to ask any questions today, but
Speak up.
speaking of what John Getty is doing, I've seen it. He has a reaction that he's put on he's got a patent on it. It uses some kind of sugar and a catalyst, and hydrogen bubbles out of it like crazy at room temperature. Apparently it's very new. I mean, are you
Yes.
familiar with his work out there? Or?
I'm familiar with the work. The problem is the availability of biomass. Remember, a typical hydrogen plant produces 100 million cubic feet a day. The energy output is equivalent to about 600 megawatts. These are very, very large numbers. To match that, you're talking about thousands of square miles of biomass going into the plant to keep it running. And that's the issue in any part of the world with high population density. There's not enough biomass to go around. So I suspect in the real world, long term, is if you can make that technology work, it'll be used in those parts of the world with a large biomass to human population ratio. It will not be applicable for Japan, Western Europe, and parts of the U.S., including the Southwest, where there's a shortage of biomass.
Okay, I have a final question. This is a department head question, you might say, but where do you get funding to work on this concept? And you say it's 14 months old, so where's your funding been from past 14 months? And in the future, what do you foresee as possible?
We're working on our NERI proposal right now. And this is one of these little spare time projects that leads up to the NERI.
Okay.
And we're fortunate in the sense that we've gotten a lot of people very excited about it, including our Sandia colleagues, put in a lot of spare time on this.
All right. I think we probably end the formal question and answer period. I see that we have several guests today, new people, visitors, and you're probably not aware, but we have refreshments downstairs on the second floor, and everyone is invited to join us for refreshments, and we can continue the question and answer period with Dr. Forsberg down there. But before we adjourn, let's give him a round of applause. Thank you.
If anybody wants a copy of the view graphs or anything else, just send me an email at Barnell.
I will do that.
It's
already on. I got another question. I'm doing some work on a care project on web business, and he's actually, he said I got trying to get documentation on estrogen. Absolutely not. What is your secret? Secret lab or what?